Let's begin the next session. Next speaker is Gadadhar Mishra from IISc.
Right.
The title of his talk is Contractive Operators and Curvature Inequalities.
Yeah, thank you. Yeah, so I am of course very happy to be here. I wouldn't have missed it anyway, but thanks Vijay for inviting me. And the scene in Bangalore, ISI of those days that Siva described so well, I would just like to say that I hung around in those times, saw the excitement, and certainly learnt a lot from Sundar. Mathematics clearly, that everybody has talked about, but a little bit of English, some spelling, and so on and so forth. A lot of it, I try to very often ask myself, if I do this or that, would someone like Sundar sort of be happy that, oh yeah, this guy has finally managed to meet some kind of standard or criterion that, he had set. So, it was a very good feeling to be there at that time. We did lots of things together, and the environment was not quite the same. I mean, he left, was rather unfortunate, and we'll talk more about that perhaps later in the afternoon. Now, coming back to this talk, I mean, my talking abilities are somewhat limited. Kalyan talked earlier about being technologically challenged. I am talk challenged. I am mathematically challenged, and every other possible way challenged. So you'll have to tolerate me. I'll try to quickly go through a couple of things. Let me be on the other side. And to make matters worse, not only that I am very afraid of Sundar, being there and trying to, I have to keep track of spellings as well as this, that, and the other. So I have put in some kind of color scheme and whatnot, which will perhaps distract you enough so that you won't notice all the math that is messed up. But that apart, I see a camera and stuff. So I hope the technology is advanced enough to correct the math that's not put in there right. So anyway, we begin with some very simple ideas, which actually goes back to the days when I was doing my PhD. There were some problems there that were left unresolved, and I'm going to report what we have been able to do 30 odd years from those days. So we begin with a holomorphic map to begin with only on a unit disk, one-dimensional situation for now, but I'll tell you what one can do in the multivariate case later on. So this is just a holomorphic Hilbert space valued function, and that's what I mean by being holomorphic. The map gamma omega inner product zeta is actually holomorphic as a scalar valued function for all vectors zeta in the Hilbert space H. For the kind of Hilbert spaces that I am talking about, this again is something that I must emphasize, that the derivative of such a Hilbert space valued holomorphic function often lies in the Hilbert space itself, thought of as a linear map. So gamma prime of omega is really a map from C to H, and I can identify that as a vector in H. It lies. You might have to make some assumptions about this Hilbert space H. I am typically assuming the Hilbert space H itself is a Hilbert space of holomorphic functions. So I have this two-dimensional vector space, if you like, vector subspace inside the Hilbert space H, and one wonders what can you do with just this very simple two-dimensional vector space. One is given by gamma omega, the other is gamma prime omega. Of course, it's a two-dimensional space, but it is a parametrized family of two-dimensional spaces. So, one of the very amusing things here is that when you are given two vectors, of course, there is no natural way in which you can order two vectors. You cannot say which one is the first vector, which one is the second vector, but we introduce an order by simply saying that we are not going to look at two vectors, but we are going to look at these two vectors along with a nilpotent matrix or nilpotent transformation. So the nilpotent transformation, of course, is defined simply by saying gamma prime omega goes to gamma omega, and then that goes to 0, and which to me actually defines an order. It says that the Gamma prime omega is the first vector, gamma omega is the next one. The next simple task is to orthonormalize these two vectors, obtain a matrix representation for the nilpotent guy. Huh? Well, okay. First, the order is there. Huh? Yeah. So that's true. But what I mean is whether you go from top to bottom or bottom to top is up to you to decide. I mean, it's the order. Yeah, I agree. Sure. The natural way perhaps is that gamma omega is the first one. Yeah. So now you get the matrix representation for this simple nilpotent matrix, and you notice that even after orthonormalization, given the nature of the Gram-Schmidt process, you will still get a nilpotent matrix, except that in this picture, which is a similarity invariant picture, the matrix would have been 0, 1, 0, 0, would see nothing about the inner product structure, whereas in this new representation, which is with respect to the orthonormal basis, a number comes up. Now, although I say a number, as I said, as long as omega is fixed, you are looking at a two-dimensional space, but you can vary omega. So this number is either a number if you are thinking of omega as a fixed point in the disk, or it is a function. It turns out it's a real analytic function of some significance. So let's see. You compute this h omega, which is a easy computation, and you get an expression like this. I just write it down. We'll come back to this in a minute. As it turns out, it's very trivial to observe that if you look at omega I plus n omega, again this will have a meaning. This operator, this two-dimensional linear transformation, is a contraction if and only if this h omega is less or equal to 1 minus absolute omega squared. Okay? So the fact that this is 1 minus absolute omega squared is again an object which is intrinsic somehow. So to give examples, you can take little l to n. Think of gamma 0 omega as this vector 1 omega squared omega n. Your derivative then is zeta 0 omega zeta bar and so on. You write that down for every choice of this vector in little l to n. And then you look at gamma 0 prime omega, it's this vector. So the gamma 0 omega is this, gamma 0 prime omega is this. I have put in a 0 to indicate that I am talking about an example. But this is of course a very special example, as you will see in a minute, and in this special example you can compute the h0. It will turn out that this h0 is 1 minus absolute omega squared, making the norm actually equal to 1. So you then observe that this little 2 by 2 matrix that you are talking about is actually nothing but the restriction of the unilateral backward shift to the two-dimensional space that we have chosen in little l to n. So to recapitulate, we begin with this unilateral backward shift. We have a whole family of two-dimensional subspaces. We restrict the two-dimensional shift, restrict the backward shift to this two-dimensional space, and we get these 2 by 2 matrices. Each one of them has a norm 1. But the point I was making earlier was that instead of picking this particular operator, you could perhaps pick a more general class of operators. You can try and find these two-dimensional spaces corresponding to that operator. You then restrict the given operator to the two-dimensional space, you get an inequality. The relationship of that inequality to the main operator is what I want to study. So you begin more generally, as I just now said, begin with a holomorphic function, and saying that it is holomorphic simply means that you have a power series expansion like that. The norm of that holomorphic function will look like this, and then you do a calculation. You do a calculation by simply saying that because this is a norm, this is inner product, this is holomorphic here, that's anti-holomorphic in some sense, you can set up this calculation. This gives you this answer, and those of you who remember 3 slides back, there was a calculation for h omega. Without going back to that slide, let me just say that this expression is that expression, except you have to take a square root and reciprocate. So square root of this 1 over that with a minus sign thrown in for good measure is that h omega. So it turns out that if you apply the Cauchy-Schwarz inequality to this guy, you look at the numerator. The numerator is the inner product of this with that but that's the product of the two norms. So you apply Cauchy-Schwarz and, no, what happened here? Okay. You apply the Cauchy-Schwarz and you observe that the numerator is positive, but because we had a negative sign outside, it turns out this expression Kw, which I would like to say is the curvature. Curvature of what? Curvature of the line bundle determined by this holomorphic family gamma omega. So omega going to gamma omega in principle gives you a line bundle, whatever that means, and this k omega that I wrote down, log gamma omega norm squared differentiated twice, is actually the curvature. The simple Cauchy-Schwarz inequality tells you that in our setup, in the context where we are talking about these things, the curvature happens to be negative. Okay, this is a certain class of bundles that for which the curvature is negative. The special example that we looked at, h omega squared, as I said, is the negative of the reciprocal of the curvature. So the special example k0 omega, the curvature turned out to be this. Now those of you recall your some stuff with this hyperbolic geometry or whatever would immediately recognize that this is the curvature of what is called the Poincare metric, and it's a very, very special kind of curvature. So it turns out that this h omega, put this way, is lesser or equal to 1 minus absolute omega squared, and that stated in terms of the curvature means property that they are contractions with respect to family of holomorphic functions, but then they will all be dominated by the Poincare metric, and that's exactly what has some kind of a meaning in the context of operator theory. In the if you take a contraction and ask, well, how can I see that it is a contraction? One of the necessary conditions is that you compute its curvature, and the curvature must be bounded by the curvature of the Poincare metric. So that's a translation, if you like. Where are we going to go with that? Well, let me just do a little bit of generalities quickly. So this is what I said, this language, the business about the curvature comes from the fact that I am talking about this is a trivial holomorphic line bundle. That simply means that I have a holomorphic function from the disk taking values on this in this Hilbert space. Okay, and then this is the Hermitian structure of that holomorphic vector bundle. So then it becomes a holomorphic Hermitian vector bundle, and the k that I wrote down in that context is the curvature. So let's define a family of operators that we want to study and that fits this situation. So T, we begin with T from H to H, which is a bounded linear operator, and we make these assumptions. We say that for each W in D, each W in D is an eigenvalue for this operator T. Omega going to gamma omega is the eigenvector with eigenvalue W. So this eigenvector is not determined completely unambiguously. You have a choice of multiplying with a constant that depends on W. The assumption here is that you can make a choice of that eigenvector in such a manner that omega going to the eigenvector at omega is a holomorphic map. Okay, this may not always happen, but we are making the assumption that you could do it. Then you assume, not very unreasonably, that the dimension of this eigenspace is 1. You can actually work with operators where the dimension is actually bigger than 1, but that's not something I'll do here. Yeah. No, not at all. In fact, with a unit vector, you won't be able to do this. Uniform multiplicity. That's why I said eigenvector, the dimension of the eigenspace is 1 for all W. Yeah.
General, you said, made a comment that that is not necessary.
Oh, the general is general. That means in the Cohen-Douglas theory back 30 years ago, they assumed it's a uniform multiplicity n. Okay, but over these last 30 years, I certainly have tried to work out various situations where the uniform multiplicity assumption is dropped. That makes much closer contact with ideals in polynomials and stuff like that. So anyway, the class of operators B1 omega, so that is the class that I call these things, any operator that satisfies this is called B1 omega, and that was introduced by Cohen and Douglas. They talked about this holomorphic Hermitian vector bundle determined by gamma that I have been talking about. So as a result, the curvature function k is a complete invariant for the operator T. That's one of the main theorems of Cowan and Douglas, that the curvature and the operator T determine each other in this situation. So you have a complete sort of numerical invariant. I wrote down a expression, I wrote down a computation, d squared d bar of log gamma omega norm squared. It's just a real analytic function. That real analytic function and unitary equivalence class of the operator T are one and the same thing. So, well, they did another thing. They provided a model for all such operators T. Remember, I said somewhere, without emphasizing, that I will assume my Hilbert space is a Hilbert space of holomorphic functions. That's not a assumption really, because all such operators T can be modeled, can be thought of as adjoints of multiplication operators on a Hilbert space of holomorphic functions on this domain omega with a reproducing kernel. In fact, that reproducing kernel is what defines that, that holomorphic section. So now, that's the kernel function with a reproducing kernel. Simply means that you have a map from omega star to omega star. This omega star is a bit of a pain. You know, you always have these two domains. You have omega and then you have this omega star with omega bar such that omega belongs to omega. Just ignore that. Pretend that omega star is equal to omega, as in the case of the disk. Doesn't make any much of a difference. But if you want to really do geometry or some, you know, then there is a serious issue that you have to grapple with. Holomorphic category versus anti-holomorphic category. Here what happens is both categories get mixed up and then you get confused enough that you can't work with either of them. Then you go to the C infinity category, work there and then push things down. But that's kind of, okay. So saying that it is a reproducing kernel, of course, really means that this function of two variables that you have, you plug in all these points w1 through wn, an arbitrary set of points, and you demand that that's a positive definite object. That's what it means to say that it's a positive definite kernel. Then you say that you have a reproducing property, which means that f inner product with k dot w. Remember, for each fixed w, this is f, I mean this k dot w for each fixed w is actually an element in the Hilbert space. So this inner product is well defined in the Hilbert space itself, and it turns out that it gives f evaluated at w. By that I mean this is the definition of a reproducing kernel. Okay, that's a demand we make. Then the reproducing property of k ensures that if you are looking at the adjoint of the multiplication operator, you will get this k dot w to be an eigenvector with eigenvalue w bar. Please notice the w versus the w bar. That's why the omega star versus omega. And so if you now write down gamma omega, by definition is k dot omega, then it will be a holomorphic section or a holomorphic map into the Hilbert space. But since this is anti-holomorphic in omega, it will be a holomorphic map not on omega but omega star. Okay. So that's the situation. So if you like, what I am talking about is a class of operators which are simply the adjoint of the multiplication operator on a Hilbert space of holomorphic functions defined on some domain omega, possessing a reproducing kernel k. That's the class of operators that I am talking about. The equivalent way of saying that in the language of complex geometry would be simply to say, rather than looking at an arbitrary holomorphic Hermitian vector bundle, you are talking about those holomorphic Hermitian vector bundles which are curves in the Grassmannian of rank 1 on some Hilbert space H. Okay, so it's a pullback. You are not looking at all possible. All right. Now to proceed, we observe. So where did that nilpotent and such things come from? So for any operator T in this class, observe that by assumption we have T minus omega I times this gamma omega. This is after all the eigenvector with eigenvalue w, so that's 0. But with continuity and everything else which I don't understand very well, apparently you can differentiate such a expression, and if you differentiate you will get T gamma prime omega equal to gamma omega plus omega gamma prime omega. Okay, so assume that this is holomorphic. or if you are in the anti-holomorphic category, if you want to be whatever, then you differentiate with respect to d bar, doesn't matter. So T gamma prime omega will be this. So if you now restrict this guy T minus omega I to the two-dimensional space spanned by gamma prime omega and gamma omega, then you get a nilpotent operator. So every operator T in this class goes with or somehow has, you know, a nilpotent operator for each omega associated with it. Okay, so NT omega is nothing but this T minus omega restricted to gamma omega. So earlier I talked about H omega and the curvature omega. So now by HT and KT, of course I mean the corresponding objects that now are coming out of a particular operator T that I have taken. This T is the T in the Cowan-Douglas class. So the backward shift is one such example again. We have said this before, but just to emphasize, the backward shift operator acting on this space, for which I told you what is the gamma prime, but you easily verify that they satisfy the properties A, B, C that was listed, and the corresponding curvature of course is K0 omega times K0 omega is this object. Okay. So what we have said so far can be put into the in this proposition that if T is a contraction in B1 of D, then the curvature of that operator is bounded by the curvature of the backward shift. Now that's easily seen, because if T is a contraction, we have already said this omega I NT omega is nothing but the restriction into this space, and we sort of have seen the matrix representation of this operator, which is just omegas on the diagonal and that HT on the upper corner. And if you do a calculation, we have said that HT omega will have to be less or equal to 1 minus absolute omega squared, which is exactly this inequality. All right. Now this was all stuff that was known many years ago. What's new? So you can play this game with a weighted shift. Rather than looking at just the backward shift, you can look at an arbitrary weighted shift. I am not going to spend much time on that, but here is a backward shift. If you like, you can compute the eigenvectors and eigenvalues. You ensure or verify for yourself that for weighted shifts like this acting on L2 through these weights W0, W1 and so on, you write down the eigenvector, convince yourself that the eigenspace is of dimension 1. So you can see that such a operator T is a contraction if and only if the sup of the weights is at most 1. The gamma omega norm squared is easily calculated, it is this. The curvature therefore can be formally written down, because this gamma omega norm squared is given to you. The curvature can be written down as d squared d omega bar d omega log of that thing dominated by the curvature of the backward shift. Assuming only that, so this is a very complicated inequality if you like, but it comes from only the simple assumption that the supremum of the Wn's are at most 1. Now this is again an example. This is true of any contraction in the Cowan-Douglas class, but I am saying for weighted shifts this is something you can do by hand. All right. What about the converse? That's the main question. That's the question that I was not able to answer many years ago. Didn't even understand what the question meant. In fact, Sundar and I had briefly talked about it again when he was back in ISI Bangalore. So what about the converse? So here is the operator T. You take a hammer, break it into small pieces. Each of the piece remains a contraction, and each of those pieces gives you an inequality on the curvature. The curvature is a complete invariant for the operator. So you should be able to, I mean, one then imagines that information about the curvature should capture everything about the operator T. So one of the questions you ask is, how do I see whether an operator is contractive or not by looking at the curvature? So one part we have discussed, namely if it was a contraction, then the curvature inequality is there for you to see. But if you have the curvature inequality, does the operator T become a contraction? So that's the issue that one tries to address, and it's not hard to see that counter examples are easy to construct. This is the reason why I worked out that weighted shift description, so that you don't feel that all this is gibberish. So here is a weighted shift with weights given like this. Notice that one of the W's here is bigger than 1. So this operator is not a contraction. You write down what the gamma omega is and therefore what the gamma omega norm squared is. Do a simple computation to see that the curvature is actually this expression. Now you will also verify that this is negative for W in the disk, and you will sort of find that you see this is actually, this expression that I have written here is the difference of the two curvatures, that is this minus that. Okay, so if you put a minus sign appropriately and so on, you will see that the curvature inequality in this particular example is valid, although the operator W is not a contraction. So the converse does not follow from just the curvature inequality, though it's a very strong inequality, but still doesn't give you the converse. So then we wonder what else can one do. Well, let's just this is the preparation for what possibly could be the answer. So we begin again, go back and sort of say that you have your holomorphic section. You write the holomorphic section in this way. Okay, write it as a power series. Gamma omega is of this form. Take the gamma omega norm squared, and gamma omega norm squared must look like this. I am just taking the inner products there. Now remember, these W square and whatnot are not really, I mean that's the variable, zeta 0, zeta 1, zeta 2 are not orthogonal or anything like that. So the norm will be of this form. Polarize to get gamma tilde z comma W in this form. So rather than writing Wj, W bar k, by polarize I simply mean replace the W by z. Replace the W by z, you get a function of two variables. It's holomorphic in the first variable, anti-holomorphic in the second variable. Now you ask yourself the question, so you know, because of our assumptions, this is actually the reproducing kernel. So you know that although this gamma omega norm squared was positive point-wise, if you polarize this way, you notice that kz comma W, which is really this inner product, which is nothing but this gamma tilde z comma W that we have defined, is actually a positive definite kernel. So this norm function is not just a positive function, but it's a positive definite function. Now the curvature itself, which is obtained by doing a log and differentiating twice, is actually a real analytic function, and part of that Cauchy-Schwarz inequality and whatnot actually showed that this curvature is, well, minus of the curvature is positive or the curvature is negative. That's what we have shown. And now we sort of look at the same polarization trick that we are talking about here, except we apply the polarization to the curvature itself. So rather than looking at this real analytic function as a function of W and W bar, we think of it as a function of Z and W, think of it as a function which is holomorphic in Z and anti-holomorphic in W. Now remember, we have said that we are looking at a class of vector bundles whose curvature is negative. Now I am going to ask.
You have to make any cut or anything?
No, nothing. I am sort of doing simply connected. Some small neighborhood is always enough. So this is the main new ingredient now. I am going to ask, is it actually positive definite? After making it, after polarizing, do I have a curvature that is not only negative, but negative definite, if you like, or with the minus sign, positive or positive definite. Stronger requirement is what one is talking about. So here is again another simple calculation. You start with any positive definite kernel on the unit disk, do the log, combine coefficients and whatnot, compute the curvature, and you find that if you make a particular choice of a kernel function, in this particular case it is 1 ZW bar, 1/4 and so on, rest of them are again 1s, okay. This is a particular kernel. You look at its tth power, again combine coefficients, this that, you can write down what this kt z comma w means. Now it turns out that if you look at t less than half, okay, then what will happen is that this kt z comma w is not going to be positive definite. Okay, this is where the notion of infinitely divisible comes in, where we say that if a positive definite kernel remains positive definite if you take all positive powers are positive. Okay, so that's what is infinitely divisible, and it turns out this fellow that I have written down is not positive definite for t less than half, which actually means that this k is not infinitely divisible. As it turns out, the corresponding curvature is, although negative definite, although negative is not negative definite. Okay, that's this example. So you cannot expect, so the upset is that you cannot expect the curvature which is negative for all our bundles to be necessarily negative definite, and somehow we make this connection that the failure to be negative definite of the curvature is somehow related to the metric being infinitely divisible. This is a connection somehow we want to make. I mean, there is a very nice little lemma which sort of connects conditionally positive definite to log k, and it turns out, as you will see in just in a minute, lower bound for t. No, t is always assumed to be positive. When I say this, I mean t is positive. Yeah. So you know, we ask that if we assume our kernel was actually infinitely divisible rather than just being a positive metric for a bundle, if we assume that it is actually infinitely divisible, that is, it is not only a positive definite kernel but all its powers are positive definite as well, then is it necessary and sufficient that the corresponding curvature, now remember curvature is a real analytic function, so you can only talk about its being positive or negative, you cannot talk about positive definiteness, but you polarize the curvature, which is a real analytic function, to obtain this analytic and anti-analytic or holomorphic and anti-holomorphic function, and then ask, can I make the curvature to be actually negative definite? Okay, that's the answer is yes. And putting all this together, of course, we try to say that here is some kind of a theorem that if you have T, which is a map from a Hilbert space into itself, which is bounded linear, satisfies A, B, C, meaning it is in the Cohen-Douglas class, and assume that the gamma tilde is infinitely divisible. That is, again, here this is only a norm. You have to polarize, and the polarized object, that is the reproducing kernel or something like that, assume is infinitely divisible, and once you assume that it is infinitely divisible, then the conclusion is T is a contraction if and only if this extreme fellow, that is the curvature of the shift and the curvature of that contraction together remain positive definite. In other words, the fact that this curvature is bounded by the curvature of the shift, you interpret as an inequality between positive matrices rather than an inequality between functions. Okay? Initially, these curvatures are only functions. So I could have said that this is greater or equal to 0 or some such thing, but rather than saying that, I want to say that you interpret this as an inequality on matrices. The proof is rather nice. The point is that if you have an operator T in the Cohen-Douglas class, as we have said, they are multiplication operators on a reproducing kernel Hilbert space, and therefore the contractivity of such an operator T is nothing but this factorization, that the object, so suppose you have an operator T in the Cohen-Douglas class, it comes with a kernel K, and if it turns out that K0, which is supposed to be this product 1 minus W bar Z times Kz comma W, is positive definite. So K of course is always positive definite, but this product you demand is positive definite. This being positive definite means that T is a contraction. Okay? But now we make the assumption that K is infinitely divisible. If k is infinitely divisible, it turns out k0 is also infinitely divisible. That's easy to see. But if k0 is infinitely divisible, then log k0 is conditionally positive definite. If log k0 is conditionally positive definite, and this is where the beauty is, there is a little lemma that characterizes conditionally positive definite. This is one sort of way of saying that there is one way of saying that if you have a conditionally positive definite kernel, you differentiate twice, and then what you will obtain is actually a positive definite kernel. Okay? So after two differentiations, that's the point, log k0, so you start with k0 which is infinitely divisible, log k0 is conditionally positive definite, differentiate twice more and you get k0 tilde to be positive definite. The converse is more or less not very much. Conversely, you take k0 tilde which was given to be positive definite and you anti-differentiate, it gives you log k0 up to an addition of a holomorphic function phi, and you do add its complex conjugate. Exponentiating, we will be able to determine what the k0 was up to a holomorphic function and multiplication by a holomorphic function and its conjugate, and from there it follows that the k0 must have been, to begin with, positive definite and infinitely divisible. Okay? So that will complete this proof, and I am done. Thank you very much.
Questions, comments?
When you say positive definite, something is positive, not positive definite. You are referring to.
When I say not positive definite,
By positive definite, we mean invertible and positive semi-definite, right?
that's right, that's right,
So the thing that gets violated when you say it is not positive definite
that's right.
is what, the invertibility?
No, okay.
Invertibility cannot be violated.
No. So that's what I mean. I put only a minus sign. When I say not positive definite, all I am doing is looking at positive definite in my sense, putting a minus sign on it, and whatever set of objects I get, that's what is not positive definite. In other words, it's a negative semi-definite which is invertible also.
It has to be invertible.
That's what I'm saying. Yeah, that's, yeah.
Writing for eigenvectors for different eigenvectors.
Right. Yeah, so what I mean is I wouldn't have to talk about it. The whole thing can be done without putting the minus sign on the curvature. Okay, so if I don't put that minus sign when I do log kk, this confusion or question won't even arise. Okay, I can just talk about positive definite. But since that minus sign is there, traditionally I keep it. That's all. It's a.
Also, you said something about differentiating by either remain d, dz,
No. D bar. Differentiating by twice, I mean it's d bar.
There's a function of two ways.
Yeah, so you differentiate with respect to z, differentiate with respect to w bar. Yeah, if you look at that conditionally positive definite lemma, that's a beautiful thing that writes it as a sum of four things, and two of them are purely functions of z and w bar. So when you do this double differentiation, those two terms go away. That's the reason why it works. Okay.
Right in the beginning, you said there is a gamma and gamma prime. You have this two-dimensional space, but it could be one-dimensional for a special.
Yeah, but it doesn't happen in the Cowan-Douglas context where you are assuming that you have a reproducing kernel Hilbert space and you are looking at the derivative of that reproducing kernel. That's linearly independent of the other one. Okay. In general, that's one of the things about jet bundles and such. That's a basic question. Most of the time you make the assumption that gamma omega and derivative of gamma omega are linearly independent. But in this case, because these are constructed in a particular way, linear independence is automatic. I mean, I can differentiate that equation, no, t minus omega gamma omega equal to 0, and ask a gamma omega plus b gamma prime omega, is that 0? Then that will force ab to be 0.
Are there results when they have infinite multiplicity instead of multiplicity?
There is. Actually, yeah. One thing is what I talked about here is, of course, does not address the question of multivariate setting, and there things are much more complicated, but we can handle it. I mean, but infinite multiplicity, was not addressed by Courtot and Salinas, not addressed by Cowan and Douglas, but following them 3 or 4 years later, Courtot and Salinas tried to redo the whole thing, and in the Courtot-Salinas picture, the infinite multiplicity is part of the story right from the beginning. Okay, so that's there.
But infinite but uniform.
Infinite but uniform, that's correct. So that's where what has happened in modern times is, that's complex geometry. But if you drop the uniformity assumption, you go into algebraic geometry.
You will have a real fiber bundle then.
Well, your bundle is no longer a bundle in the sense that the fibers will keep jumping in dimension, and that's what happens when you start looking at arbitrary ideals inside a polynomial. You see, typically what you will do is you will take a ring of polynomials, you look at an ideal inside that ring, and you localize with respect to some object, that some module or something. So when you localize, what will happen is those localization dimensions thought of as modules, their dimension will keep jumping from one place to another, whereas in the case of the vector bundle, the way to describe it is something pre-modules or something. There is a 1-1 correspondence. That freeness is what will get affected when you don't assume uniformity. So
Any other question? So let's thank Gadadhar once again. So we'll resume after 5 minutes.